So this part here is the main application. So this is what we hope. If you're looking at linear differential operator, d squared and some function in front of d and some function in front of I. If you're looking at this differential operator, this is the differential operator associated with the linear, second order linear differential equations. If you're staring at this type of operator, and if you can factor into product of these two operators individually, this is the first order linear differential operator, first order linear differential operator, and second order linear differential operator. If you can factor through this product of two first order, then you can handle this first order using the integrating factor. Then after that, and you can handle the second operator. So this probably very convincing line of attack to the second order differential, if it's possible. So you can see it here. It's not just the multiplying things out. It seems like we're just multiplying this out, d squared. If these were just numbers, then you will have definitely px plus qx. And if this were a number, what's supposed to show up here is just a px times a qx. But as you can see, there's a qx, q prime x shows up, and that's causing a big trouble for us. Where that come from? When this one is operating on that part right here, product rule will cause an additional term, and that kicks in here. So the way this one unfolds, it's similar to numbers, but there's this additional term, and that's the main difficulty of given quadratic expression in operator algebra to be factored into this part. However, if these px and qx are constant functions, instead of functions multiplied in front of I, function is multiplied in front of I here in the second factor. If these were numbers, a and b, then you can see if you unfold this one, you have this b prime. B is a constant, derivative becomes 0. This is a 0. So the way this one unfolds with a constant coefficient in front of I is exactly behaving just like the numbers. If these d and a and I are numbers, and you will unfold this product of two binomial expression exactly to this form. So if these things are numbers, constant coefficient, the operator algebra behaves exactly like algebra and numbers. So here's an example. D minus a and d plus 2i multiplied in operator notation. If you unfold it, carefully going through that, keeping the d, linear, acting on from the left, and all that thing we just did. If you do it carefully, you can verify that it's just simply d squared plus d minus 2i, just like the numbers. Then this amazing thing happens. So look at here. This is really amazing, because this linear order differential equation, linear second order differential equation with a constant coefficient here, and these are constant. If you apply function to this part, it becomes exactly like this: y double prime plus y prime minus 2 times the function y that is applied there. So when you see this second order linear differential equation like this with a constant coefficient, and you associate this linear operator with a constant coefficient and squared, quadratic, and you know this one is equal to that, and this one factors through this first order operator, then you go to another first order operator. So this one is nicely factored through that. And this idea is called a decomposition of an operator. If something, you're looking at it here, is complicated thing is done to this function y, and we kind of decompose it in first, something that we studied a lot, the first order, we know how to completely answer this type of operator. We first do that, and then do this one later. So we decompose it of this complicated action into a sequence of two actions, each of which we completely understand. If you have taken the linear algebra, and we do the same thing, if there's a complicated looking matrices, then we can decompose it into a product of simpler matrices. So each of them we understand it better. Therefore, we understand a whole lot better of what's happening to this complicated looking operator. So here's an application.